Hi everybody, I'm Jay Paycheck, the marketing manager here at DMS. We're gonna give everybody about a minute and then we'll have Tim and Chad come up here and we'll start the webinar. Just wanna give everybody a minute so they can join us. All right, everybody. Like I said, my name is Jay Paycheck. I'm the marketing manager here at DMS. We're doing something new. This is the first time we're going to be doing a webinar via Facebook Live. Normally we use a different platform, but we want to see if we can maximize our viewers and really try to get that information out there. We're going to have Tim and Chad kind of talk to you guys, not even kind of, but really give you guys a pretty good understanding of calibration. So without further ado, I think Tim's going to come up now. Oh, I do want to mention that this video will be available afterwards on our Facebook page as well as our YouTube channels.
All right, hello everyone. Thank you for joining us today. We're going to be going over machine alignments in every aspect, not only how we align them, how you can do checks yourselves. So first I'll introduce myself. My name is Tim Collender. I am the Service Department Supervisor here at DMS. I am also one of our traveling field engineers. I'll be joined today by Chad Frankenberger, who's one of my most senior field engineers. So like I said, today we'll go over the 5-axis alignments as well as linear straightness, squaring, different things like that. So first I'll introduce Chad and he's going to go over his first part.
Hi everyone, I am the aforementioned Chad. So first thing we're going to go over is the tools that we would be using out in the field and some tools that we would recommend you guys having so that way you can do some of these checks on your own as well. The first thing we got is our machinist level. This is to check the levelness of our machine. From there we have a sweep indicator and a sweep arm. Both of those are to check the spindle alignment. Then we have our plunge indicator and a mag base. These are to check various checks within the machine for alignment. And then we also have a tooling ball and a dowel pin, which makes it easier for us to get measurements during our 4th and 5th alignment. Go ahead to the next slide.
Okay, and before I go too much into this, I'd also like to mention that if you would like to purchase any of those previous tools, you can reach out to us at customer service at dmscncrouters.com and we can help you get these tools if you would like to purchase them. Okay? So first I want to kind of discuss, before we get into the 5-axis alignment part of the machine, which I'm sure many of you are interested in, first we want to discuss the main 3 axes relationships and how to make sure that those are perpendicular to each other. Because if you don't have perpendicularity between X, Y, and Z, none of the alignments are going to matter at all. Okay, so click. Okay, so we have 3 main relationships of perpendicularity on any machine, whether it be a 3-axis machine, these are your main 3, or a 5-axis machine also requires these as a minimum. So we have a relationship between X and Y, a relationship between X and Z, and a relationship between Y and Z. Okay? So we consider the X to Y relationship, if you look at your machine, you would consider that your bridge squareness, right? The examples we're gonna go through today are on a typical standard machine configuration, which would be X is the bridge transverse travel, and Y would be either a moving table or a moving gantry movement, okay? The backbone front to back on this particular machine would be Z with respect to Y, as it's Z moving down needs to be perpendicular to the table or the gantry travel. Okay? And next is side to side, which is going to be the Z perpendicular to the bridge travel, side to side. Okay. Okay. Next slide.
So one of the first things that's very important for when we're checking these alignments is making sure we have a level machine. The way we do that is we have a base plane that we use off of the linear rails that is attached to the base of the machine. Like I say, rails for the base of the machine. And we usually use a Hamar 3-plane laser to do this, but you can also do this check by using a machinist level on the bridge rails as well as the base rails, and just use multiple fixed points to make sure we get all the alignment that's necessary to ensure the machine is level. So some consequences of not having a level machine are as follows. One, you will not have a repeatability overall whenever you're doing your part cutting and anything like that. Excessive stress on rails and bearing blocks, which then will cause for replacement parts in order to make sure your machine is running appropriately. And then excessive stress on the base weldments. So you can cause your weldments to go bad, and I mean, generally speaking, you don't want that on your machine at all. Okay.
All right. So let's look at the level of the machine, starting with just the base of the machine. So we're using a moving table type machine right here. So if we eliminate everything else, we can just see the base rails and what everything, the rest of the machine is all relying on these rails themselves. Okay? So when we say level the base, we don't necessarily mean it has to be done to earth level. It's, as long as it's on a plane to itself, the machine will cut accurate parts. It's recommended, however, that you go to earth level, because then you always have a point of reference for future checks. So if you aligned it to a plane that wasn't earth level, and then somebody else checks it a few months later, they think it's completely out of whack, stop production, when in fact it may have been true. So it's always a good idea to get it to earth level, that way all future checks show that the machine is still in good shape or bad shape. Okay? So to visualize what I mean by a plane, just imagine, so go ahead, Jay. So imagine taking a piece of material that was perfectly flat, that covered all the rails of the machine. If you laid that on top of all 4 rails in this situation, it should be perfectly flat, no wobble, and that would tell you that all services and all travels at that point are consistent and true. Okay, so now we're going to dive into actual adjustments on the machine, and also the order. We all remember in math there was an order of operations. Well, there's an order of operations to understand when aligning and squaring a CNC machine. Okay? So first, we want to make sure the base is level, as we just previously discussed. The next point is squaring the bridge to the X-plane. After that, we will square the backbone front to back. After that, we'll square the backbone side to the side. And then once we're confident in that, we can move on to our 4th and 5th alignments. So the order is important here, because the backbone side to side, you have to loosen bolts to adjust. So by doing the front to back first, which is a shimming adjustment, every time you loosen the bolts and tighten the bolts, that will always repeat back to where it was. And then both of these are all riding on the bridge, so you want to make sure you start with the bridge first, because if you move the bridge on the columns, you could be affecting this, this, and this. So that's why our level, or our order, is very important on the steps. And we'll also discuss order in the future. Once we get into 4th and 5th alignments, order is also very, very critical.
So the second step that Tim just mentioned was squaring the bridge. For this one, we are adjusting our fixed axis, the x-axis, in the direction of y. So the way that we would go about this is, generally speaking, this is a general layout of our bridge bolts. We'll see 6 on each side. The way that we would make these adjustments, and we'd usually use a Hamar 3-plane laser to find the deviation for the bridge. But how we would do it is we would break loose all these bolts that are not circled. Then we would leave this bolt tight as a pivot point and remove this bolt completely to allow us to adjust for that deviation we saw previously. Now, not everyone has a Hamar laser capable of doing this there in their factory, so we do have quick checks in order for everyone to at least get an idea if their bridge is square. So the easiest way is using that mag base and a dial indicator to check the front of your table. The best way to do that is either attach the mag base to the spindle or the yoke of the spindle, and then bringing it to one side of your table, either the left or right. Make sure the dial indicator is touching, and then zero out the indicator. From there, you can move across the front of the table, and if you see a linear deviation, then you can be pretty certain that your bridge is out of square. And using similar method as before, you can make that adjustment to get it back into square.
Thanks, Chad. And so now, once the bridge is square, now we will move on to the alignment of the z-axis itself. And as I previously discussed, we want to start with our z relationship with y. Okay, so whether this is a moving gantry or in this case a moving table, we want this to be perpendicular. The way we achieve this is by shimming, and so there's always been some confusion of where to shim if we're doing this through remote support or whatever. And it seems obvious that you want to shim the backbone to the ZRails. Well, that's not the case. In that case, all you're doing is shifting the angle. It's still going to be traveling out of square, right? So where we want to shim is the whole backbone carriage between the bridge rails. So we'll determine, typically with a Hamar laser, like I said, you can also, if you have granite blocks available, you can use granite blocks. So long as you can cover the full length of the travel of the Z. So then you can align the granite, the bottom of the granite, to your Y plane, and then indicate off the 90-degree part of the granite, and then make shim adjustments as necessary to get your Z perpendicular in the Y direction. And like I previously discussed, the reason we do that now is the next step is side to side. And in order to do this, you would do the same thing, except for now we're doing X. So you could set up a granite block plane on the bottom this way, and then indicate off the side. And then you can shift the backbone on their 16 bolts here. And similar to the bridge adjustment, we would leave one bolt tight as a pivot point, and then there is an adjustment wedge that can be placed either on the right side or the left side on these two holes here. And the way it works is it creates a wedge between the backbone and the top of that running block, and it'll actually lift. So if we were trying to tilt it this way, we would leave this one tight, and we would increase the wedge here, and that would straighten it this way. And then once we retighten, since the shims stay the same, they're precision ground, the front to back didn't change, and now our side to side is perfect.
So when you have a machine crash, there are 4 things that you can be expecting from the cause of that. One of them is your rotary axes. Their home positions may be lost, which could be a combination of various things within the head alignment that could be out of whack. The next is the bridge position on columns may shift as well. Your Z position on bearings may shift, and your rails can be pushed out straightness. And right here we have a video showing some rails after a crash. These are specifically the Z-axis rails. If you'd go ahead and play the video. And this is a simple check that you guys all can do if you're ever concerned with a crash, and Tim will be going into detail about it later. But as you can see, as we're jogging down the Z-axis, we can see deviation on the dial indicator as we progress down. And if you guys don't know by now, that is definitely not good. You do not want to see that on your dial indicator at all.
Now that previous video showed the ZRails. And using that same setup, where, can you go back to the previous slide? Yeah. So what you want to do is attach your mag base to the most lowest point of the Z traveling carriage, extending out so that the indicator is only looking at the rail. And what you can do is one rail at a time, use that same indicator. You know, it started out pretty straight, use that as your 0 point. Loosen bolts and adjust and get one straight. And then you would do the same thing on the other side, except for you could use a bearing similar to what I'm about to show you on your bridge rails. The Z-rails are the trickiest of all the rails on a machine to get straight again. Ideally, you would want us to come out with a laser to where we could put them back in a perfect straight line on a laser line. But it can be done. Me and Chad have both done this in the field without a laser, and we've gotten them back to straight. It can be nail biter trying to get the Z-rail straight. Okay? So bridge rails, they're less likely to get knocked out of shape or bent, as we refer to it, because typically the Z takes most of the brunt of an impact, but it also depends on the travel the machine was moving when it crashed. But on the bridge rails, on top of the bridge, we have a machine surface that was done when the bridge was initially machined at the factory. So we can pull one of the bearings off, attach our mag base and plunge indicator to it, find a nice flat spot, because typically the crash only happened in one location of the travel. So first you want to zero your indicator where you're seeing 0, 0, 0, 0 for a good amount of distance. And then you keep going, and once you start seeing error, take a Sharpie, mark a line. And then keep going. When it goes back to 0, put another line. Now you know your window of where it's out of square. So now you just remove the plastic bolt covers and loosen all the bolts inside that window, and then starting from one side or the other, one by one, using your indicator, and then pushing or pulling on the rail. You can typically remove a bolt in front of where you're adjusting and stick a pry bar inside there to kind of press the rail up and down. Got a 0, lock that bolt, move on to the next one, and systematically move down the line, and then go back and double check. And once you're 0 all the way across the bridge, now you can move to the bottom rail. And now we have our top rail that we just leveled is nice and straight. Now we just move our plunge indicator to the top of the lower rail, and we do the exact same process, and we can get both bridge rails nice and straight. It doesn't require a laser on site. This is something pretty much anybody can check and align themselves. Okay. So now that we're sure that our X is perpendicular to Y, is perpendicular to Z, now we can start discussing the 4th and 5th axes of the machines. So first, a little overview of fourth and fifth. They're always referred to fourth and fifth. They're always a letter though. So typically, fourth axis is always going to be a C axis on any DMS for sure. The fifth axis is the spindle rotation, and that can be set up as either an A axis or a B axis. Most of our machines are set up as B axis, fifth axis machines. A way to kind of determine how this should be set up on the Cartesian plane, you can kind of see it outlined here that the A rotates around X, B rotates around Y, C rotates around Z. Another way to look at that is here's our three main X, Y, Z. A rotates around X, B rotates around Y, C around Z. Our secondary linear axes, so maybe you have a twin table machine, or it's a motor that is synchronized with a master motor for a moving gantry. So moving gantries require two motors, one on each side to move. So in that case, the U would be slave to the X, the V would be slave to the Y. W and Z, you might have a two backbone machine. So your secondary Z is going to be W. To ensure that all your rotations are correct, I've seen this happen before. A motor gets replaced and somehow the windings of the motor were different than the original motor, and now we're not getting parts because the motors are turning the wrong direction. They're turning the opposite of the way they should be. So a way to verify that is always going to be to follow the right-hand rule. And the simple way to do that is you stick your thumb in the axis positive direction, and your fingers rotate around in the way the C should rotate in that case. And in Y and B, stick our thumb in Y, rotate B, X, rotate if we were doing A. Okay. So now we're going to start going through our step-by-step process of the fourth and fifth alignments. So similar to squaring the machine and aligning the machine, there is a very particular order that must be followed here so that you're not negating a previous adjustment that you make. So first Chad is going to start talking about our first adjustment, which is the C plate.
So our C plate right here, it's going to be the first component that's connecting our backbone to all of our rotary components. So it's ideal that we get this aligned first to make sure that the rest of our adjustments are going to be based off of that. And what we're aiming to do is make sure this C plate is going to be parallel to the XY plane for all of our future measurements after that. So you can see over here the basic setup for it is with a dial indicator at the bottom of the yoke and with, the mag base at the bottom of the yoke with a dial indicator pointed down. From here, we rotate it around all four corners of the machine, so 45, 135, so on, just adding 90 degrees to each one. So when we see any deviation, the way that we would be adjusting it is these three bolts located at each of the corners. Two of them are set bolts that lock it into place, while the middle one, located right there, is going to be the adjustment to where we can actually change the deviation that you see from this measurement. And like I said, it's very, very important that we make sure that C plate is going to be parallel with the XY plane, because we want to make sure that all of our measurements, we're going to be working up from top to bottom to get everything aligned.
Make sure you have a flat table or granite.
For this one, you want to make sure you have a flat table or granite. There are methods to work around that, but ideally that's going to be the best way to make sure you get a 0 all the way across the board reading.
Okay, so now that we're sure that this gearbox, the C gearbox, is rotating perfectly along our XY plane, now we want to make sure our yoke is square to the Z center line. Okay, and the way we do that is first you're gonna find your C home position. So you put an indicator with a dial, you zero it at B90, C0. Okay, and then without moving in or out in this direction, so in our case on this machine, we would not want to move the Y at all. We can lift the Z straight up, flip our B to minus 90, come over, come down on the same dial until we see 0 and 0 on both sides. Once we're sure that those are the same, now we come down to B0, go over the same pivot point. And what that means is as the spindle is rotating, it is following that imaginary plane that's going through there, okay? So if you see any deviation at this point, it's okay to see some deviation because it just may mean that this is not square to the Z right now. So you write down, you document what was your error at B0. So say it was negative 5 thousandths, okay? Now we're gonna lift up, flip C 180 degrees. Come down, do the exact same thing. Zero your indicator at B90, flip it over to minus 90, come down, adjust C as needed to where you have C, or a 0 on both B90 and minus 90, come down again to B0, come across the indicator, and notate your error. Ideally, if you saw minus 5 thou at C0, you want to see a positive 5 thou at C180. If your signs are the same, that tells you that your Z in the front to back alignment is out of square. So that's the kind of, one of the main points we want to emphasize on this webinar is that a lot of these problems can be found on site, and then determine whether you need us to come out and address or if you have the equipment and lasers to address it yourself. This is just a way, and this is why whenever we come out for preventive maintenance, we're doing an overall check of the machine, and we don't use a laser, but we can find out, is the Z out of square, okay? Now you can do the exact same test, because that told us our front to back was out of square. If you want to do the exact same test to see if you're out side to side, then you would just do it at C90 for your first part, C270 for your second. And then stand up B to 0, do the exact same thing. So, and the reason, if your signs were the same on the error, is what that means is the Z, is if you think about it, you're moving up and down in Z as you're doing this check. So Z is down here, and then Z has to raise up when you go to 0. So if it is not square, you're moving into or out of the indicator. And if you tried to shim to adjust the 5 thou on one side that was negative, when you rotate C, now you just made your previous 5 10. So you will never get a perfectly aligned machine if the Z is not perfectly square. Oh, yeah, that was the second part. So that was showing when B is at 0 and where to place, this is where we would place the shims in between these two plates to properly get the yoke square.
Alrighty, so the next step that we'd be looking at is sweeping the spindle, which would be checking our spindle alignment, and that's where our sweep indicator and our sweep arm come into play. For this alignment, we're similarly checking the spindle as we did for the backbone to see if it's out like this or if it's out like this. If we're seeing it out like this, our first adjustment would be looking at the B home position, which when we're reading it side to side, we should expect equal and opposite values, which we can adjust the B position and then use parameters within the machine to reset that home position. So now that we have a good B0. Similarly to the backbone, when we see a deviation from front to back, we'll be needing to add shims to our machine to adjust for that error. And what we'll be doing is in between this spindle plate as well as the B rotational plate, we'll be either applying shims to the top or bottom of that in order to adjust for the deviation. Generally speaking, we use about a 3-to-1 ratio, which means if we see a 9 thou error from front to back, we'll use a 3 thou shim to adjust for that error.
Okay, so next we have spindle centered. Okay, and what we mean is on the Z itself, the center or rotation point of the spindle, I like to use an example, is on that line so that everything is equal, right? So if this is my center, my Z, and my spindle was shifted a little bit as we rotate to 90 and minus 90, we will see deviations by using an indicator as shown here. So we previously set B0, so we know that when B is at 0, it's perfectly straight. We know it's flat at 90, we know it's flat at minus 90, okay? So by using an indicator, checking on both B90 and B minus 90, the difference we see, so if we zeroed on one side and we flipped it over and we saw 10 thou of error, then we would split that difference 5 thou. And the way you would do that is you would place your indicator right on the center, as close as you can to the center point, and then we have adjustment tabs. They're not in this picture, but typically there's an adjustment tab. You can see the bolts right there with a set screw, so that you can loosen the mounting bolts and then shift this plate, the same two plates previously discussed. You would shift, and then now that we loosen the whole spindle, we need to revisit B0, so we need to put our sweep in arm indicator back on there, ensure that our B0 hasn't changed, make any adjustments as necessary so that B0 is true, then go back to 90 and minus 90, and we should have 0 and 0 on both sides. Once we have 0 and 0 on both sides, now our spindle is rotating exactly on the center of the Z.
Is that?
Yeah.
Gotcha. Okay, so this is kind of, oh, here we go. So here's the tabs that I was talking about that we would use to shift it on the plate. Okay. Later, and this is kind of a more of a physical way of showing that where the tip of the tool is in the center of the spindle, and this is the center of the rotation of Z, right? So what we're trying to do is get that perfectly in line here. This is a snippet of the manual, because there are actually machine parameters that we could set. So if we knew this was 5 thou, we could put 5 thou into data 2. And when you have RTCP active, or your Kinetics are active, the machine will compensate for that to keep the spindle tip true.
So this is the last mechanical adjustment that we'll be making to our machine during the 4th or 5th alignment. The rest of them will be parameter changes in order to set 0 positions as well as adjust the kinetics. So this one is we're getting our spindle center relative to the C axis rotation, which is also known as concentricity. So what we're doing is we have our dial indicator on our dial pin, and we rotate C around to see if we can find any deviations at the points 90, 180, and 270, and then as well as verify 360 is matching 0. The way that we do that is we have these adjustment blocks that are located right underneath the C gearbox right here. And this picture only shows one, but there's actually one on each face of that yoke assembly. So the way that we would adjust this is anytime the dial indicator is showing a deviation, we will have to break loose these bolts to allow the shift, and then we use the 2 blocks that are parallel with the dial indicator, so making sure they're in line and we're shifting it in and out of the dial indicator. And we'll keep rotating, checking, and making adjustments. And like I said, the big thing is we want to make sure we're making the adjustments on the blocks that are parallel with the dial indicator, since it's going to be fixed.
Okay, so now that we have made all of our mechanical adjustments, it's a good time now to make sure that B0 is true again. So I would typically always put my sweep indicator back on the spindle, sweep the table, make sure you have a good flat surface to reference, just like the very first step. We want to make sure we're referencing off a flat plane on the XY. And then also our C home position. We just, in that previous step Chad discussed, we just shifted the whole yoke around on bolts So now our C home, our C0 location may have changed. So at this point you want your indicator pointed horizontal on a dowel pin, B90 being -90 at C0, you should have zeros. Adjust C as necessary to where you're 0, 0. And then that can be put into your reference shift parameter if you have an incrementally encoded motor, or you change the physical location of the 0 of the motor if it's an absolute encoded motor. So now everything is good. So now we can start looking into putting this all together to make sure that when you have a tool in the spindle, the tip of the tool is where the spindle will rotate on accurately, which we call RTCP, or in some cases just TCP, tool center point. Okay? So the first part of that to determine is pivot distance. What pivot distance is where's the end of the spindle and where's the pivot point that it's turning on. How much distance is this? Okay? So the first thing you do is put in this example, this is a 1/2" dowel or a 1/2" index pin. You want to zero your indicator on the high point of that dowel. And then you want to set a position, it's not going to be 0. You're not going to set a preset of 0 because we want to be actually the center. So in this case, I would preset Z to 0.25 as this is a 1/2" tool. So that puts me, if I go to Z0, that would put the center of the dowel right at the same 0 point. Okay? Now we jog Z up, rotate B to 0, and we indicate off the most lower point of the face of the spindle to achieve the exact same 0 that we had previously. Now all you have to do is look at the screen of your controller, and it's going to tell you whatever number it shows Z, what position, that is the pivot distance. Okay? And that is the number that we would put into T data 1 or X data 1, depending on if you have an 8055 or 8065 controller. Okay? And then the way the controller uses that number is then you will measure your tool using your tool length setter or manually measuring your tool from the face of the bottom of the tool holder to the tip of the tool. The controller puts those two numbers together. Now it knows exactly how far it is from the center of the spindle to the tip of the tool so that it can properly rotate on just the tip of the tool. Okay? So next. Okay, and this is kind of more of an example of how we can fine-tune the kinetics. Okay, so we have all these data. Data 1, like I said, is the pivot distance. So that's the distance between here and here. Data 2 is our spindle center and between, it's hard to see on this one. Okay, so here's our center of our Z. And data 2 is actually the center of the tool. And then we also have concentricity adjustments. So you can, that previous step, so that when you're rotating C on the side of the tool, it's staying perfectly concentric. So you can shift it in X or in Y. And we have a procedure we can provide. As long as you have a tooling ball and a plunge indicator, you can do all these checks and make all these adjustments yourselves. Okay? So once we've fully aligned the machine, all the rails are straight, we've gone through the 4th and 5th alignments, we've gone through our kinetics checks, everything is good. Now we'll see a video of how this all looks on the dial indicator to see how accurately it rotates on the tool. Okay, and for that to work, that stayed within 1,000th of deviation through all those movements. That is using all 5 axes simultaneously, which is why each step is critical and each one affects the next. But that's our goal right there. This is what we like to see on our machine. Okay? And so that pretty much covers our overview, so now we're available for questions.
Okay, so the first question is, can you give an approximate tolerance we need to be within for each adjustment?
Okay, so the tolerance, so we have a written procedure, like I said, so just like the kinetics procedure, we also have a full documented procedure for doing the 4th and 5th alignments. It is outlined in there what the tolerances are. We typically like every adjustment to be within 1 thou. That way, when we're doing the kinetics adjustments, we're only tweaking it 1/4 of a thou, 1/2 thou, things like that, and we get a perfect machine out of it. So really, I mean, there's no set tolerance. It should be, you know, what are your part tolerances? I mean, some machines are used to cut wood that could have a tolerance of 1/16 of an inch, and then we have machines doing aerospace where, you know, they're down in less than 1 thou or 2-3 thou on all their stuff. So the more accuracy you need out of the machine, the more accurate you need to get every step done.
And like Tim said, most of the steps we're looking within 1 thou for all of our adjustments, especially if we're on site doing the adjustments.
Right, there's just some adjustments, especially when you're involving shims. So like Chad said on the aligning the spindle, it's a 3-to-1 ratio. So if we're 1.5 thou, there's no 1/2 thou shim that I know of, right? So you're just gonna get it as close as you can, and then you address it with kinetics. That's where the kinetics come into play, is getting the adjustments you can't make mechanically.
Awesome. All right, so Mark asked, if we can't get the spindle aligned with B, should we still do spindle aligned with CZ axis?
So, and I believe he's referring to, you can't get the spindle centered with the Z. So if, say you're out of, your bolts are running out of holes and there's no more room for it to adjust. At that point, you would want to introduce your kinetics and allow the kinetics to make that adjustment. We have machines with heavy-duty spindles require an offset yoke or a heavy-duty yoke, where it's impossible on the concentricity part, the spindle centered in C rotation, that we have to use kinetics, and we're using numbers of over 2 inches. And then once you turn on your RTCP, you'll see it stays perfectly true. So any mechanic, most all, I'm gonna say most, I don't wanna commit to all of them, but most all error can be corrected with kinetics, provided the machine has a good base and good straight rails and everything's square.
And like Tim said, we want to make sure we do everything on our part for the mechanical adjustments before we start looking into the kinetic adjustments. Because if we can get it aligned as best as we can mechanically, then it makes the kinetics a whole lot easier, and we're not using the machine to change the mechanical deviation.
Right. All I can say is, in my experience of doing this for over 6 years now, I haven't run into a spindle yet that I wasn't able to get centered C to B. So if that's not possible, I would want to question what else could be possibly going on with the machine.
They probably should call us then.
Call us, or, you know, it sounds like something's probably not square.
Okay. All right, well, I guess there's only one more question, and it's on a scale of 1 to 10, how nervous was Chad for this webinar?
I think
I'll give it like a solid 7. Yeah, not gonna lie. Yeah,
I think I've seen improvement over our last video.
Yeah.
And just to say, the last video was internal only.
Right.
It wasn't on the World Wide Web or on social media at that point.
Yeah. And so then Leonard asked, are the slides you shared available for later reference? I'll, just so you guys know, this is Jay, the marketing manager. This video will be available, and I'll make sure the slides are available as well on the Facebook Live, as well as our website, as well as, and I'll also try to I'll upload this video to YouTube as well.
Right.
So,
And if you have any questions, like I said earlier, we also have an email in our customer service department.
what's the phone number and email address?
Okay, so the email address is customerservice@dmscncrouters.com, and the phone number is going to be 855-266-5063. That will put you in touch with Gay, and all of this information, like I mentioned, we have documented procedures for multiple machine configurations. There's different yokes, different spindles. So all we would really need is the serial number of the machine that you would like the procedures for, and then we can forward any of this information to you.
Awesome.
And if you need any of us to help you walk through any of it, we're here to help you out. Just like if you need more of an explanation on each of those steps, we're more than willing to walk you through it and tell you exactly how we would do it and tell you what we're looking for.
Yep. And just a couple more things to go over. So I wanted to readdress when you're indicating on the front edge of the table as your reference to make sure your bridge is square. It is, as the machines get older and older, and as maybe floors have settled, they've been leveled multiple times, it is possible that that front edge, and the reason we're using that as a reference is because once we squared the machine at the factory, we machine the table with the machine. So that's why we can use that as a reference. But if that's changed over time, and you indicate that and you see a huge number, but yet you're getting good parts, you don't see any reason why it's not out of square, it's a good idea to get an end mill and just run it along the front edge. Give yourself a good reference point.
And going off that, I mean, a lot of these checks, one time that you should really be considering looking into this is my part is not coming out right. That should start raising some questions. Do I need to start looking at the alignment of the machine?
Right.
So always keep that in consideration.
And I think, a lot of these checks, the intent also was machines get crashed, right? It's just part of the machining world. The problem is the operators a lot of times are hesitant to admit that they had a crash, and then all of a sudden one day you're making good parts, the next day you're making bad parts, you don't know why. You're trying to figure out what happened. These are some simple tests to say, well, if you saw the video of the dial indicator of the bad rails, okay, well, something happened. That gives you a good indication something happened in the machine. There was some event that caused the machine to be out of square. And so the next step may be to try to address it with some of the techniques we went over today, or at that point you might want to just arrange a service call and have one of our certified techs come out with the lasers and all the tools to get your machine running good parts. That's our goal. We want our machines making parts, making everybody money.
Absolutely.
All right, thanks guys, and everybody, thank you for joining us. And like I said, we'll make this available for everybody. Have a wonderful day. Thanks, Tim and Chad.
Thank you guys.
Thank you guys.